Hello and welcome to my channel. My name is Zess and I make Ren'Py minigame tutorials. And as usual, I would like to take a moment to thank all of my patrons who are continuously supporting my work and my channel. And this month there's also a few more patrons that have joined. So thank you so much for joining and supporting my work and my channel. It is very helpful and also very appreciated. So thank you so much. In this video, I'm going to show you how you can create a sliding puzzle in Ren'Py, where you have a bunch of horizontal and vertical wooden blocks together with a red block that can be dragged up and down or sideways. And the goal for this puzzle is to unblock the path of the red block so that it can reach its destination. This type of puzzle requires you, as the visual novel developer, to come up with a block formation that can be solved by the player. To do this, I'm going to show you how you can work with an image editing software, such as Photoshop, to create the puzzle images and work out where each block should go. Now you don't have to do this if you don't want to, as you can just use the assets and script that I have created. However, this will only create one puzzle and you might want more in your game, and in that case, you will want to watch the puzzle creation guide of this video as well. But if you don't want to have to figure out where to place each block to create more of these sliding puzzles, then you can always become a patron of mine in the voting tier or higher, where I will have a few extra puzzle formations that you can use as well. With that said, let's go ahead and have a look at the preparations that you need to do before we get into the video. You're going to need a fresh Ren'Py project in the size 1920 x 1080 pixels using the latest version of the Ren'Py engine. You are also going to need the assets for this tutorial, which you can download from the description box below. It is also good if you have at least some basic knowledge in Python programming to understand the coding better, but you might still find the tutorial interesting and useful either way. The finished script for this tutorial can also be downloaded by my patrons in the tier supporter or higher. So with that said, let's go ahead and get started. So the first thing we're going to have a look at is how you can create the actual graphics for the minigame puzzle. For this example, I'm using Photoshop, but you can of course also use any free alternatives if you don't have Photoshop. You just need to make sure that the program that you're going with is able to show you the coordinates of each of the images on the canvas. So in Photoshop, for example, we can click on this move tool up here and then have one of the layers with the graphics selected, and then we can simply click on one of these white handles on this blue border in order to get the coordinates of this specific graphic on the canvas. And those coordinates we can see up here, where we have the x coordinate and y coordinate right here. Now we also need to be able to change the origin point of where these coordinates are based on, and that we can do with this little square right here where it says reference point location. And in this case we need to base it on this top left corner instead of in the middle, so we're just going to click there instead, like so. So now we can see that this specific block is located at 277 on the x-axis and 87 on the y-axis. And these coordinates we're then going to be using inside of Ren'Py in order to place each of the blocks inside of the game. And because we're going to be using sprites inside of Ren'Py, each of those sprites have their anchor point at the very top left corner right here. So that is why we're going to need to base the coordinates on this top left corner. Now for the actual creation of the images of the puzzle, you first of all want to make sure that the canvas is the same size as the Ren'Py project, which is in this case 1920 x 1080 pixels. Then the background image can of course be anything you want, as it doesn't matter that much to the actual minigame, but it should of course fit the size of the canvas to fill the entire background of the game. Then for the actual minigame components, it's good to take some inspiration from games like this that already exist. So if you Google, for example, unblock sliding puzzle, you'll find a few examples you can take inspiration from when you decide on sizing the frame and blocks. I found that the frame of the puzzle is usually a perfect square, so that is what I went with. And I also added a border to the frame that is 15 pixels wide. And if you also decide on making a border for your frame, just make sure that you note down how wide it is, because we're going to need it later on when we code the game. The blocks are usually two different types with two different sizes. We have a long and a short horizontal block and a long and a short vertical block. For the horizontal blocks in this case, I made one to be exactly half of the width of the frame, and the height is simply determined by how many times we could potentially fit this block if we were to stack it several times on top of each other. So in this case, I just picked a height that I thought looked good, and then duplicated the block several times until I reached the bottom of the frame. And if the blocks didn't fit all together, like this, then I would select them all and resize them at the same time on the height until they all fit snug inside. But if and when you are going to do this yourself, You just want to make sure that the duplicated blocks that you're stacking on top of each other are not going to leave any gaps between them, and that is just to make sure that the resulting block is going to have a perfect height. Then for the short horizontal block, I just resized the long one to be just a little wider than half of the width, and then checked to see if I could stack several of them sideways while fitting inside of the frame. And if you find that they don't all fit perfectly in the width of the frame, of course with no gaps between them, then you just need to resize them like I showed before, but on the width instead. And for the vertical blocks, we just need to rotate each of the horizontal blocks so that they are vertical instead. Now for the tutorial, we're only going to be working with one type of red block, which is going to be a short horizontal one. So I duplicated the short horizontal block and then simply made it red instead of brown. So now we have all the blocks that we need. We also need a goal for the red block to be dragged to in order to win the game. And in my case, I decided to make this a colored bar that fits on top of the border on one of the sides, like so. And since the red block can only be dragged sideways, we only need one type of this goal, which is going to be this vertical one. And it should also be the height of the red block as well. Now for the formation of the blocks, you want to start with placing the goal on the right side of the frame on the actual border. And I have found that other minigames like this usually place them exactly 2 horizontal blocks down from the top of the frame. And the red block should be, of course, on the same y-axis as the goal. And usually I found it to be around 1 or 2 vertical blocks away from the left side of the frame. Once you've done that, it is time to lay out other types of blocks into the frame that is going to block the path of the red block from reaching its goal. You of course just need to make sure that these blocks can be moved in a way that allows the user to solve the puzzle and therefore clear the path. When you are doing this, you want to make sure that there are no gaps between the blocks or a block and the inner part of the frame. But you also want to make sure that the blocks do not overlap each other on the edges either. And the reason for that is, once we are going to place each of the blocks inside of the game, and one block is overlapping another block by too many pixels, that block might get stuck or behave incorrectly. But we are going to implement an offset value in the collision detection of the blocks of 2 pixels in case we don't have everything aligned perfectly. So as long as you get the positioning of the blocks as neatly as you can, it is still okay if some blocks happen to overlap each other by a pixel or 2. So here's a short clip of a block formation that I thought worked well in my testing, as it requires several steps in order to clear the way for the red block. And then once you have a block formation that you're happy with, you also want to go to the layers panel and make sure that you name each of the layers according to what's on them. In my case, I made sure that each of the blocks are named according to their orientation and size. But I will also put up a list on the screen so you can see what I've named each of the images if you want to name yours the same. And we're going to be using these file names inside of the code as well. And then you also want to make sure that you group all of these blocks together into a group folder that you can call, for example, Puzzle 1. And then when you want to create more block formations, you can simply duplicate this group, call it Puzzle 2, and then just rearrange the blocks to something different. And if you're using Photoshop like I am, you can make the export process a lot quicker by right-clicking on one of the layers that you want to export and then choosing Quick Export as PNG. Then when the save prompt opens up, you'll have the file name already filled in according to the layer's name. And remember to also note down each of the block's coordinates on the canvas using the method that I showed you early on in the video. And a tip to make things a little bit easier is to group each block that share the same y coordinate into the same row. So in my case, I have 2 blocks on the first row, which is a short vertical block, which I have written down as SV, and a long horizontal block, which I have written down as LH. And then I have added the coordinates for each of those blocks as well. So now that you've gotten a few tips on how you can create the actual artwork for the minigame, we're going to go ahead and open up the main script file of the Ren'Py project, and I'll show you how to code it. So here I have the main script file open of the Ren'Py project, and as you can see, I've already written down all of the code necessary in order to make this minigame work. But don't worry, I'm going to go through each section of code and explain what it does as well. But before we go ahead and do that, you also want to make sure that you have added all of the necessary images into the images folder. So the main thing we will be working with in Ren'Py to make the blocks draggable, but also able to collide with each other, is something called a sprite manager. And the sprite manager, which is another type of displayable in Ren'Py, allows us to create sprites, which are basically images. But these sprites we can manipulate in various ways throughout the game based on user input, which would be much more difficult to do if we were to use some of the other more common list variables available, especially because of our particular type of minigame. So to create one, you first of all want to make a new variable. In this case, we create it in the start label and set it to be equal to a sprite manager object. I've called the variable block_sm, where the sm stands for sprite manager, and I named it that because the sprites we are going to create with it are going to be the blocks. We want to assign two functions to this sprite manager. One of them are triggered when it needs to update, and the other one runs when a user event happens in the game, such as when they press a key on the keyboard or clicks with the mouse. With the event function, we will therefore detect when the user wants to drag a block by using the mouse, and with the update function, we will move the block to where the user drags it. In it, we will also implement collision detection and detect if the red block has reached the goal. Together with the sprite manager, we also need a list that we can add the sprites to that we create with it. This will make it easy for us to access blocks later on in the code when we need to do something with them. We initialize the list as an empty list for now, as we're going to fill it with the correct blocks at a later point. Next, we have 7 variables that contains images for the different parts of the puzzle. These are the horizontal and vertical blocks, together with the red block and the goal. We define each type of image with different variables that we can refer to later on when we create the sprites. I've named these variables according to the corresponding block orientation and size, but I've shortened the words horizontal and vertical to just one letter, just to make the variables a little bit shorter. We also have 5 variables that contain the sizes of each type of block as well as the frame, and we store these sizes as tuples, where the first value is the width and the second is the height. This is so that we don't have to memorize them and retype them every time we need them, as we can just refer to these variables. And we need this specifically to make the collision detection between the blocks and the frame work as intended. Then we also have a variable that stores the position of the frame according to the position it has on the canvas in Photoshop or whichever program you're using. And this one will also be important for the collision detection as well. The next variable, called current puzzle, is used to keep track of which the current puzzle is to make sure the puzzle will be shown to the user. We set this to 1 at the start of the game, but then when the user has solved the puzzle, we can set it to the next value to show the next puzzle. The variable after that, named clickPause, is used for the dragging functionality of the blocks. We will fill this later when the user initiates a drag with the correct coordinates, so for now it will be a list with zeros instead. And those are all the global variables we're going to need for this minigame. Below that, we can see that I have set the game to jump to a label called Scene1 as the first thing it does. So let's go ahead and have a look at this label next. So here we can see the Scene1 label, which is an example of how you can transfer the user from a label in your visual novel to the minigame. In this case, the label has some simple dialogue, then a custom function named createBlocks is called, and this function is responsible for setting up the current puzzle by creating the block sprites and position them according to the puzzle formation. After that, the screen that actually shows the minigame is called, that contains the displayables such as the frame and the sprites. So this is the order that you set up the minigame. First you call the function that creates the necessary sprites, and then you call the screen that shows the minigame to the user. So now that you know that, let's have a look at the function that creates the block sprites called createBlocks. So here's the createBlock function at the very top of the script. And for Python functions to work properly in Ren'Py, so we can call it from various places in our script, we need to wrap it in an init Python block, like so. Then inside the function, we first of all use the global keyword together with the block sprites list variable, so we can change its content inside of the function. Since this function is going to run every time we want to set up a new puzzle, we want to first make sure we remove all the previous sprites from the previous puzzle. Otherwise, we will get both the previous puzzle's blocks as well as the new ones. To do that, we need to destroy the sprites in the list so they get removed from the game. And for that, we have a function in Ren'Py available to sprites called destroy. So we'll make sure that we call this function on each sprite in the list. Instead of manually having to type out each sprite that needs to be removed, which will be a long and unnecessary process, we will create a for loop that will run until all the sprites have been destroyed. The for loop will run as many times as there are items in the list, and the block variable will contain the current sprite for the current iteration. Then we just need to call the destroy function once for the current sprite in the loop. After that, we have destroyed the sprites, but we haven't yet removed them from the list. That might be a little confusing, but I won't go into the technicalities of why that is. Just know that the list will still have access to the sprites even after we have destroyed them, and we need to empty the list completely to get rid of them. So for that, we set the block sprites variable to an empty list, like so. Now to make sure that the sprite manager catches up without the sprites have been destroyed, we need to update it by calling the redraw method. We supply it with the value 0 to tell it that we want it to run immediately and only one time. That will then also trigger the update function for the sprite manager to run. So with that done, we go on to the next section of the function where we actually create the sprites. For this tutorial, as I mentioned before, we only have one puzzle, and to create this puzzle, we first want to check if the current puzzle variable is set to 1. If it is, then we want to create the first puzzle. So inside of this if statement, we go ahead and create each block and position them according to their coordinates we noted down before. This we need to do manually because each block is different and has different coordinates, so to automate this with a for loop isn't going to work for us in this case. We start with the first row of blocks, and to make it easier to read the code later on, we will section each row with a comment. Then we create the block that is first in this row, and in order to create it, all we need for that is this section of code right here. Here we are using a function available to sprite managers called create, and then we supply the image that we want the sprite to use. Since the first block in the first row, according to the notes, is a short vertical block, we will supply it with the image for that block. So now we have created a block sprite, but because we want to add this block to the list as well, we make sure to add this code inside of the append function available to our list. So by saying block sprites.append, we are adding the block sprite we created inside of the round brackets to the list. So after we have created the block, we're going to need to create a few attributes for it as well. That's going to help us to quickly and easily be able to tell what kind of block we're dealing with in the code for the dragging and collision detection. So in this function, we will initialize these attributes for the sprites, so we can access them later on in the code and use them in different ways. The first attribute is going to be called type, and we'll set it to be equal to the block type. In this case, it is a short vertical block, so I have abbreviated the string value to SV. An attribute can be thought of as a variable, as it works much in the same way. This attribute is however only available for this particular sprite and can only be accessed through it. Next, we have a size attribute that will store the size of the block, and we set this to be equal to the variable that stores the size of this block type. We do this so that we can quicker get its size later on by simply referring to this size attribute. We also need to keep track of when this block is being dragged and when it's not, and to do that we have an attribute called drag, and we set it to false to start with, as when the game starts, the block is not being dragged. The next two attributes are actually default attributes already available for sprites in Ren'Py. These attributes are being used by Ren'Py in the background to actually place the sprite in the game. So here you want to add the x and y values according to the coordinates you noted down in your text file or in the text file I provided for this tutorial. The last custom attribute that we need is going to keep a track of the initial position that the sprite was in before it got dragged, and we need to know this value in order for the dragging functionality to work correctly. In this case, the x and y coordinates are added to a list where the first value is the x coordinate and the second one is the y coordinate. And they should be the same as the x and y attribute values, as they are the initial coordinates of the block when the game starts. So now we have created the first block in the first row that has the necessary attributes we need and the correct initial coordinates. Now we just need to repeat this for all the other blocks as well. So next up, we have the second block in the same row. This block is a long horizontal one, according to the notes, so we tell the create function of the sprite manager to create a sprite with the image of the long horizontal block. This is of course also added to the list as before, using the append function. The attributes should have the values according to this specific block. In this case, the type attribute should be equal to LH, which stands for long horizontal, as this is a long horizontal block. And the size attribute should be equal to the variable that contains the correct size accordingly. Make sure you set the x and y coordinates to what you have in the notes and add those to the initial pulse attribute as well. And then you just continue like this for all the other rows or blocks. When you get to the red block, which is in this case in row 3, you set the type attribute to red and use the size of the short horizontal block for the size attribute. At the bottom here, after the last row of blocks, we also have the goal. This one we add as a sprite to the block sprites list as well to make it easy for us to detect when the red block collides with it. For this sprite, we don't need all of the attributes that we used for the blocks because this is technically not a block and shouldn't be dragged. So for this sprite, we do the same as before in terms of creating it, but we use the goal image instead of a block. The type attribute should be equal to goal in this case, and then for the x attribute, we use a calculation to determine its placement in the game. Since the goal should be at the right side of the frame, we set the position to be at the same x coordinate as the frame plus the frame's width minus the width of the border. So here you can see an example of when we need to know the frame's position and size to position another sprite correctly. Then for the y coordinate, it should be the same as the red block. So to keep this simple, we can just copy the y coordinate from the red block and add it here too, as they should be on the same row. Then the size attribute should be the size of the image of the goal, which you can check in your notes if you added it, or just check the size in the properties of the image. Remember, first comes the width, then the height. So that is all for the create blocks function. Now let's go on to the event function, where we'll detect when the user holds down the mouse button to start dragging a block. So here we have the blocks events function, which is also in the init Python block. An event function for a sprite manager expects to have 4 arguments or parameters available to it. The first one is called event, and this one will hold an object that contains information about what user event has just happened in the game. If the user clicks with the mouse, for example, this parameter will tell us that was the event. Then we have an x and y parameter, and these ones will hold x and y coordinates of the mouse as the event happened. The last parameter, called st, will tell you how much time has passed since the sprite manager was first shown in the game. We will only have use for the first 3 parameters for this minigame. Inside the function, we are going to supply the global variable clickBoss that we created in the start label with the coordinates of the mouse according to the x and y parameters. So because we will change it, we need to declare it as a global inside of the function. After that, we want to check if the event that triggered this function to run was from the user holding down the left mouse button. So to check that, we create an if statement. In the if statement, we access an attribute available to the event object called type, and this attribute holds information about the type of event that just happened. So we compare it to see if it is a mouse button down event. To do this, we access the mouse button down attribute of the Pygame object available in Ren'Py. If the type attribute of the event object is equal to the mouse button down attribute of the Pygame object, then the user is holding down a button on the mouse. Inside of that if statement, we then check if the button for this event was the left mouse button. That's because we only want the user to be able to drag a block if they're using the left button. We do that by comparing if the button attribute of the event object is equal to 1. In case you're curious and didn't already know, the value 1 represents the left button, 2 represents the middle button, and 3 is for the right button. Then inside the if statement, we have a for loop. This for loop is used to find the correct block that the user is holding down the mouse button on. Since we have many sprites in the block sprites list, we make it quicker to find the correct one by looping through each block in the list. Then we compare with an if statement if the mouse is colliding with the current block in the loop, because if it is, then the user wants to drag this block. In this if statement, we have a few conditions. The first condition checks if the current sprite in the loop we named block is not the goal. Because if you remember, we added the goal sprite to the block sprites list as well, and since the goal isn't a draggable block, we make sure to not test it for collision with the mouse. So we check if block type is not equal to goal. If that is the case, then the if statement goes on to the next condition, and here we are checking for the actual collision. We do that by checking if the current block in the loop has an x coordinate that is less than the x coordinate of the mouse. If that is true, then the mouse is further to the right than the block sprite. Then we also check if the x coordinate of the mouse is less than the block's x coordinate plus its width. And if both of these conditions are true, then that means that the mouse is within the block's bounding box on the x-axis. Then we do the same check on the y-axis, and if all of these conditions combined are true, the mouse is completely within the bounding box of the current block in the loop, so we know this one is the one that the user wants to drag. Now inside this if statement, we want to make sure the block is ready to be dragged. And for that, we set the drag attribute of the block to true. Then the clickBoss variable is going to contain the x and y coordinates of the mouse according to the event data we have available. After we have done that, we need the update function to start moving the block according to the movement of the mouse. And in order to trigger it, we call the redraw function of the sprite manager. As I mentioned before, the redraw function causes the sprite manager to update itself and its sprite children, which is done in the background code of Ren'Py. This will also cause the sprite manager's update function to run as well. Then the last thing we need to do is to break this for loop because we found the block we are going to move, so we don't need it to continue. So this is how we detect when the user wants to drag a block and set its attributes to the correct values. Now we also of course need to make the block stop dragging when the user releases the mouse button, otherwise we'll have the block stuck to the cursor indefinitely. So for that we create another if statement. In this case it's an elif statement because it should only be checked if the other if statement does not evaluate to true. For this if statement we check if the event is instead mouse button up, and we check it the same way as before by accessing the Pygame object, and then this time the attribute called mouse button up. Then inside of that we have a for loop again that loops through the block sprites list, and with the if statement inside we check if the current block in the loop has a drag attribute that is set to true. Once we get to a block in the loop that has its drag attribute set to true, this if statement will evaluate to true and the code within runs. In this case we set the block's drag attribute to false because now we no longer want to drag this block. We also need to update the initial position of the block to the new position that the user has dragged it to. So we set the x and y coordinates of the block to the initial position attribute. Again, now that we are done with this for loop, because we found the correct block to use and did everything we need with it, we break the for loop so it doesn't keep running when we don't need it to. With that done, we have now completed the event function. So now let's go ahead and have a look at the update function that is responsible for moving the blocks. So here we have the update function, and this function takes one parameter, which is st, and as before, this one contains the amount of time that has passed since the sprite manager was first shown in the game. We're not going to be using it inside the function, however, as we don't need it. Inside the function, we declare the current puzzle variable as a global, so we can change its value later on if we want to. After that, we have a for loop, and as before, it's looping through the block sprites list, so we can find the block that the user wants to drag. By using the enumerate function available in Python on the list, we also get access to a number which represents the current loop. This number we store in the variable called b1, which stands for block 1, and then we also have the block variable again that holds the current block in the loop. Inside this for loop, we first of all have an if statement that checks if the current sprite in the loop is not the goal, and if its drag attribute is set to true, because if it is, then we have identified the correct block to move. Then we have a local variable to this function named offset, and this variable we're going to be using in the calculations that determine if the drag block is colliding with another block. This will make sure the collision detection allow for a 2-pixel overlap to make sure the blocks don't get stuck when they shouldn't, in case we didn't align them perfectly. Before we can start dragging the block that the user has chosen, we want to detect what type of block this is. This is so that we can lock the movement of the block to an axis according to its orientation. So therefore, this next line of code is an if statement that checks if the block is a long or short vertical block. Then inside that if statement, we have another local variable, which is called distance. This variable contains a calculation that determines the distance between where the user clicked on the block and the new mouse coordinates where the user has dragged the mouse to. This distance is therefore how far the block should move. We use the getMousePos function available in Ren'Py to get the current position of the mouse, and the clickPos variable, as you might remember, contains the coordinates of where the user clicked on the block. Since it is a list with an x and y coordinate, we grab the y coordinate by adding 2 square brackets after the variable name together with a 1. We do the same thing with the tuple that the getMousePos function returns to get the y coordinate. So now that we have that, we want to go ahead and move the block according to this distance value. We do that by setting the y attribute of the block to its initial y position minus the distance. And this will make sure the block moves according to the user's mouse movement. We don't want to simply subtract the distance from the y coordinate of the block, because then the block will just keep moving in the direction that the user dragged it, even if they stop the movement. This is why it's important to base the movement on the initial position of the block. Now that we have moved the block, we want to check if it's colliding with another block or the frame. Because we don't want the drag block to be able to overlap another, we need to check if they're colliding so we can make sure to move it back until it no longer overlaps. To do that, we need another for loop, which is inside the previous for loop, and this one will also loop through the block sprites list so we can find another block to check for collisions with. In this case, we have a variable called b2 and stands for block 2, together with a second variable called block 2 that contains the current block sprite in this for loop. Inside this loop, we can now check if b1 is not equal to b2, because if that is true, then we know that we are dealing with 2 different blocks from these 2 for loops. So let's say that the first loop up here is on its first iteration. That means that the b1 variable will be equal to 0. Then the second for loop is on its first iteration too, which means its b2 variable is also equal to 0. That means that both of the loops currently have the same sprite active in the corresponding block variables. We don't want this because that would mean that we're trying to compare if the drag block is colliding with itself. In the next iteration of the second for loop, but still on the first iteration of the first loop, the b2 variable would be equal to 1 and b1 still equal to 0. This would instead mean that we are now working with two different blocks, which is exactly what we want. So by checking if b1 and b2 are not the same number, then we can go ahead and check if the two blocks from the two loops are colliding. Because the drag block is a vertical block and can only be dragged up and down, we want to check if there's a block somewhere above it that will block its path. So in the next if statement, we first make sure the sprite in this for loop isn't the goal. Then after that, we have the rest of the conditions wrapped into round brackets. The first two conditions here checks if the drag block has an x-coordinate that's within the x-coordinate of the right and left side of the second block. If it is, then we know for sure that our drag block has at least one block above or below it that it could be colliding with. Now we also need to check the left side, so for that we have an OR operator here that makes sure that if the conditions before it are not true, then maybe the conditions that comes after are. These conditions do the same thing as the previous ones, we just make sure to check the left side of the drag block instead of the right. So now we have an if statement that checks the left and right side of the drag block to see if its path above or below is blocked. If that is the case, then we now need to check if our drag block happens to overlap any of these, because if it does, then we need to move it until it doesn't. We do that by first checking if it's overlapping a block above it, and for that we simply check if the drag block's y position is less than the bottom side y coordinate of the second block. And if it is, then they are overlapping. So now we need to move the drag block back down until it no longer overlaps. And we do that by setting its y coordinate to be equal to the bottom side coordinate of the colliding block. Then we update the initial position attribute of the block to the new position and also update the click pos variable to the new y coordinate of the mouse. And that is all we need to do for a drag block that is colliding with a block above. Next we have an elif statement that instead checks if the drag block is colliding with a block below it. For that we check if the bottom side of the drag block has a y coordinate that is more than the y coordinate of the second block. If it is, then again we need to move the block away from it, and this time we move it up so it sits flush against the top of the colliding block. Then again we update the initial position attribute and the click pos variable with the new coordinates. With that done, we also need to make sure the drag block isn't overlapping the edge of the frame above or below it. And for that we have two more elif statements which have the same indentation as this if statement right here. Here we first check if the drag block is colliding with the edge of the frame above it, and we do that by checking if its y coordinate is less than the frame's y coordinate plus its border width. Then if it is, we simply set the block's y coordinate to sit flush below the border of the frame and then update the initial pos attribute and the click pos variable as usual. The next elif statement checks if the block is colliding with the frame below it instead by checking if its bottom edge y coordinate is more than the frame's bottom edge y coordinate minus its border width. If that is true, then we set the drag block's bottom edge y coordinate to sit flush against the bottom edge of the frame minus its border width. Then we update the initial pos attribute and the click pos variable once again. So now we have a complete collision detection done for vertical blocks. In the next section, just below that, we check if the drag block is a horizontal block instead. This section of code does pretty much the exact same thing as the vertical collision detection we did above. So instead of rewriting much of the code again, you can simply go ahead and duplicate the vertical section of the collision detection and then paste it underneath. Just make sure this section of code, which starts with this elif statement, is in the same indentation as the if statement that checks if the block type is a vertical one. Then you also want to add a third condition to this if statement that is going to check if the drag block is the red one. And that's because the red block is also a horizontal block that can be dragged sideways, so we include it into this section. Now remember to also change the block types that you're looking for. So instead of looking for LV and SV, you want to change it to LH and SH. You also need to update the other code so it works for horizontal blocks instead. So for this distance variable, we want to change the calculation to get the distance between the x coordinates of the mouse, so we add a 0 inside the square brackets instead of 1. Same with the next line, you change the 1 inside the square bracket to a 0 instead. With the rest of the code that comes after, you want to continue and swap each 0 and 1s inside the brackets. So if there's a 0, you change it to a 1, and if it's a 1, you change it to a 0. Each x and y attributes need to be swapped around as well. So for example, with this if statement right here, you want to check the block's y coordinates instead of x. So all of the conditions inside of here should say block.y and block2.y instead. The size attributes will need to check for the block heights instead of widths, so you want to swap these zeros for 1s. With the rest of the code, even the code inside the if statements need to be changed the same way. So with this if statement, instead of checking if the drag block is colliding with another block on the y-axis, you need to check it on the x-axis, because the drag block is horizontal and can only move sideways. Then inside the if statement, you move the block on the x-axis instead of the y-axis, so you want to swap the y attribute for the x attribute. And the ones inside the square brackets should of course be zeros instead. And then you continue with the rest of the if statements and the containing code the same way. Once you've done that, you need to add an extra if statement to the bottom here that will check if the block that's being dragged happens to be the red one and if the second block is the goal. That's because if the user has dragged the red block all the way to the goal, then we need something to happen next, because now the user has won the minigame. We also have a third condition here that checks if the red block's right edge x coordinate is the same as the goal's x coordinate, because if it is, then they are colliding. This if statement is also in the same indentation as the other if statements right here. Also note that this is a normal if statement and not an elif statement, and that's because we need Ren'Py to check and evaluate it even if one of the other elif statements evaluates the true. Inside that if statement, we can now tell Ren'Py to jump to a label that will progress the visual novel to the next thing. So for that, we use the jump function available in Ren'Py and tell it to jump to the label named solved puzzle. The last line inside this if statement is a return statement with the value none. With update functions, you can tell Ren'Py if you want it to run this function again after a certain amount of seconds since it last finished, and that you can do by using a return statement followed by the number of seconds that you should wait until it runs it again. This return statement should be the last thing you add after all the other required code, because after it, no other code in the function will run. Since the user has dragged the block to the goal, we don't need the function to keep running automatically, so we add the return statement with the value none. This will make sure that the function will not automatically keep running when we don't need it to. So now we have finished the collision detection for the blocks entirely. The very last thing we need for this function is another return statement that will run in all cases where the red block hasn't reached the goal. You want to make sure to add it in the same indentation as the first for loop in the function. This return statement is followed by the value 0 to make sure this function will keep running every millisecond to move a block according to the user's mouse movement. If we don't have this in a function, then it will not keep running as the user is dragging a block, so the block will only move one step and then stop. Another thing I like to mention is that within this last if statement right here, you can also set the current puzzle variable to contain the value for the next puzzle. Here I have commented out that line because for this tutorial we don't have any more puzzles to show. But by setting the variable to another value, you can make sure the next time you show the puzzle screen to the user, they will see that puzzle instead of the first one. For this example, I just set the variable to be equal to 2, but it would be better to set it to plus equals 1, because that will make sure the variable increase in value every time the player solves the puzzle. Otherwise, it would be stuck at 2 and only show the second puzzle. With that said, the label that we jump to after the user has finished the minigame is just a simple one with 3 lines of code. As you can see here, the first line simply shows a background image, then a piece of dialogue is shown where the character says to finish the puzzle, and then we simply go back to the scene 1 label. And that is actually it for this minigame script. You should now have a functional sliding puzzle minigame to put into your visual novels. Before we end the video, I'd also like to give some debugging tips for those of you who might experience issues with your block formations. As I mentioned before, if you aligned your block pieces a little off to where they might be overlapping too much at the start of the game, they might get a bit stuck or behave weirdly when the user starts to drag them. Let me show you an example of what could happen if you have a piece overlapping another by more than 2 pixels. So here we are back in the create blocks function, and specifically in row 4 of the blocks. Now let's say that the last block in the 4th row, which is this one, has its x coordinate a little more to the left. So instead of being at the x coordinate of 882, we would instead set it to 879, which is 3 pixels more to the left. Then when we launch the game and try to drag this block upwards, we can see that it seems to be working, but then it will do this. That happens because in our collision detection for vertical blocks, we look to see if the drag block is overlapping another block above or below it. When the block's bottom edge reaches just above this block, they're now technically colliding, and the drag block is prevented from moving any further down. That's because its left edge is overlapping the bottom block's right edge. And that's obviously no good because this hinders the minigame from working correctly. So if you do find this type of thing happening in your game, you'll want to make sure to check the coordinates of your blocks. You can test by moving the blocks away just a few pixels from the neighboring blocks and then run the game again to see if it works. I hope that this tutorial has been interesting and that you have found it to be helpful. And if you have any questions about the coding, feel free to leave a comment down below. I also have a Patreon page where you can download all of my previously finished tutorial scripts in case you're interested. The script for this tutorial can also be downloaded by my patrons in the tier Supporter or higher. Thank you so much for watching, and I hope to see you in the next video.